This second chapter of Geology for Everybody is intended to describe to you how geologists classify rocks. The fundamental criterion is where and under what conditions did the rock form. In a broad sense, there are only three environments that form rocks. So, classified by the origins defined on this chart, they are sedimentary, igneous, or metamorphic. As this second chart shows, any one of these three classes of rock can be converted to another, but some transformations are more likely than others. The most rapid require decennia. The slowest demand millions of years. We begin with sedimentary rocks. This very helpful chart shows how sedimentary rocks originate and are classified. At the top, their source is postulated to be an igneous rock, but it could just as well be a metamorphic or an existing sedimentary rock, or any combination of them. The key to the origin of sedimentary rock is weathering. Here are some pictures of weathering phenomena. Weathering is the disaggregative and destructive processes of wind, water, and ice on rocks that are at or near the surface of the earth. It is mechanical or physical when there is no change in the chemical composition of the weathered material. The major agents in this form of weathering are expansion and contraction, caused by repeated heating and cooling, frost action. When water freezes, it expands and wedges the rock apart, exfoliation or spalling. Chips, plates, or shells of rock separated by differential stresses produced by the release of pressure on the materials comprising the rock. It is chemical when the breakdown is caused by the action of chemical agents. These are oxidation, hydrolysis, solution, and cation exchange. Solution of limestone is by far the most common of chemical weathering phenomena. Almost all of the products of weathering are transported by water, and as shown under this sketch of shoreline and sea, are sorted by grain size and by precipitation of dissolved minerals into three subclasses, of which two are joined to comprise the siliciclastic category. As the chart indicates, both visible grains and clay-sized grains are clastics, for the term includes all rocks composed of dewatered and compressed particles ranging in size from very large boulders to the smallest grain of clay. The chemically precipitated rocks are differentiated into two groups, chemical and biochemical. Dewatered minerals like salt, gypsum, and chert are a discrete chemical group, and multicellular plant remains are considered biochemical. As these slides show, the particles of sand-sized clastic rocks are named and graded according to size, here defined by the Wentworth scale, and also are described and named with respect to the degree of roundness of the grains and how nearly uniform they are in size, their degree of sorting. Together, these criteria, along with their content of minerals other than quartz, give clues as to their maturity, how long they have traveled, and the distance from their source. In addition, these mechanical clastics have many other names, qualifiers, and subdivisions. for these rocks range widely in their degree of compaction, and many of them have been infiltrated by fluids that enter the intergranular spaces called pores, where they deposit minerals that bind grains together more tightly and tend to fill the intergranular spaces. Here are pictures of the more common types. First, those rocks that appear to lack this intergranular filling called cement. Mudstone and shale are compacted clay-sized particles. With increasing pressure, these fine-grained mudstones develop facility, platy lamina, and become shale. Progressively coarser-grained clastic rocks are named siltstone, sandstone, and conglomerate. Their size limits defined by the Wentworth scale pictured. When conglomerate pebbles are angular, the rock is a breccia. When feldspars make up an appreciable percentage of the sand-sized grains, the rock is an arkose. Add micas and fine-grained dark-colored material, and it is called greywacke. Both of these relatively untraveled entities were formed near their igneous or metamorphic rock source. Of the cemented clastics, some rocks composed of clean sand-sized quartz have their void space completely filled with silica. They are an unmetamorphosed type of quartzite called orthoquartzite. The intergranular space of other sandstones or siltstones may be partly or completely filled by spar calcite or any other form of calcite, by dolomite, siderite, gypsum, anhydrite, hematite, limonite, barite, celestite, or any other water-soluble mineral. In this highly magnified scanning electron microscope image, the dark sub-rounded quartz grains are surrounded by spar calcite, and clay-sized particles may constitute more than half of the volume of a rock, so the grains of quartz or feldspar are completely enclosed. It is a dirty sandstone or a sandy mudstone. Why are clastic rocks classified and described so minutely? Scientific accuracy is laudable, but the main reason is economic. Detailed analysis of rock constituents is indispensable in the search for and development of valuable mineral resources. In a rather narrow spectrum of clastic environments, minerals as sulfides, oxides, and carbonates comprise exploitable deposits of gold, copper, silver, uranium, iron, and molybdenum. This sketch names and illustrates the environments in which sedimentary rocks occur. Clastics predominate in rivers, their deltas, in adjacent portions of the continental shelf, and in turbidite, that is, submarine flows denser than water of previously deposited undersea sediments. Where the supply of clastics is meager, deposits are predominantly calcareous on the continental shelf and in lakes, caves, and hot springs on land. In the deep sea, one prominent element is clay-sized oozes containing a host of small unicellular organisms that under anoxic conditions on the sea floor are preserved in black shales that can generate the precursor of oil and gas. In the past, the factors regulating the deposition of sediments were no different from those of today. Consequently, from a study of the characteristics of any suite of sedimentary rocks, geologists can make inferences regarding their origin, their environment of deposition, and their subsequent history. Adding dip and strike to these data make possible a reconstruction of tectonic events and associated changes in sea level. If fossils are present, they may aid greatly in an interpretation of environment. All these data are essential in the search for commercially exploitable minerals and incidentally in reconstructions of paleogeography. Part 2 of Rock Classes Chemical rocks will appear shortly.